All right, hi everybody, and welcome to the next webinar in our Driving Reliability series. My name is Stephanie Fauché, and I'll be your moderator for today. Today we're going to be covering improving automotive electronic performance in harsh service environments. A few quick housekeeping notes before we get started. You're welcome to ask questions at any point during the presentation. Please feel free to use the Q&A box down in the right-hand corner of your screen or the chat box, which can be found towards the center of it. Today I'm joined by Calvin Jennings and Dominique Troop. Calvin is our Senior Sales Director, and he joins us with over 20 years of automotive experience. He's worked in manufacturing and design engineering at Ford, as well as business development with companies such as Continental. Dominique Troop is an application engineer with our team. She has over 5 years of automotive experience working with Tier 1 companies and OEMs as both a quality engineer and a senior materials engineer. With that, I'm going to hand it over to Calvin Jennings to get us started.
Hello, welcome. Thank you for joining us today. I'll take you through the first half of the presentation, and then I'll turn it over to Dominique, where she'll get more into the technical side. So we'll talk about the agenda. So first, what are the current and future trends of the automotive electronics? The challenges of these trends for engineers. How to protect the electronics from the harsh automotive environment. Why engineers are turning towards thin film technology. Finally, the benefits of paralleling. So here's a chart showing the growth of electronics over 80 years, from 1950 to 2030. You can see in the 50s, electronics made up just 1% of the vehicle's total cost, not much more than a radio back then. Then by 1980, about 10% of the total cost was electronics. Electronics were starting to become prevalent for controlling the engine, transmission, yet power windows, power locks, things we see as basics today. Since the 80s, electronics as a percentage of total vehicle costs are nearly doubling every 20 years or so, even as the cost of the vehicle is increasing. I've seen this personally in my career, where the electronics have taken a front seat, not only in prevalence, but also in reliance upon their capabilities and performance. When I first started, I had project responsibility for electronic spark control. It was on engine, and then it got integrated into the electronic engine controller. So all of these were at the time where electronics were becoming integrated into other electronics. So, and also now if you look at your instrument cluster, right, back in the 80s, it wasn't much more than just simple gauges for fuel, speed, and engine RPMs. Now you have big graphics displays showing your turn-by-turn navigation, all of these HMI type interfaces that are all in your gauge. So today, the electronics are much more sophisticated. Now we have ADAS, the Advanced Driver Assisted System devices, that really weren't prevalent in vehicles previously, right? You have blind spot detection, you have radar, LiDAR, you have cameras for backups around view, your lane keep, you have adaptive cruise control, even park assist. Right? So every year, there are more electronics being added to the vehicle. And every year, brands and consumers, they're counting on them for critical functions. So our mission at HZO, it's to work closely with the OEMs and tier suppliers to help them design a more robust solution to protect the critical electronics from the harsh automotive environment. Here's a list of just some of the electronic modules that have become critical in today's vehicle. And these all have some sort of protection. I chose modules that I found that have either partial conformal coating, complete conformal coating on either side, conformal coating with seals. These are found under the hood, the interior, the exterior. These electronics are everywhere, and these are just the ones I found that have some sort of coating on them. So from convenience to criticality, it's important that all of these function consistently. So it's estimated that by 2030, the electronics will account for more than 50% of a vehicle's total cost. You saw that in the other chart. And then we'll go through and you'll see all these different devices and applications. All you can see where you're going to have a huge jump from 2020 at 35% up to 50% by 2030. And it's not just the components that are changing. The powertrain has seen a major change as well, with a shift towards electrification. That includes hybrids, battery electric vehicles, and even fuel cell EVs. And then in addition, there's new EV-only OEMs that entered the market, like Tesla and Rivian, for example. And they're all competing with and against the traditional OEMs. So right now, it's estimated that there's about 1 million plug-in electric vehicles operating on American roads. And then by 2030, it's estimated that there'll be between 10 and 35 million electric vehicles. So you can see from 2020 to 2030, all of these increase in electric vehicles. So with the advent of electric and autonomous vehicles, we're seeing the future appear before our eyes. It's estimated that driverless systems will comprise 25% of the global automotive market by 2040. The autonomous vehicle market is expected to be about 500,000 units in 2025, and then projected to reach 6.9 million by 2030. So you see another huge increase on the autonomous side. And this increase is triggered by various factors, such as the need for ease in driving and the increased concern for safety and security. This leads to demand for high-end technology, resulting in increased demand for semi-autonomous and autonomous vehicles. Globally, it's estimated that the autonomous vehicle market will generate around $67 billion in economic value and $60 billion in societal benefits by 2030. And the driving force behind all of this is the electronics. They're the driver behind this technology. There's all these electronic control units that process the information from the various sensors, the eyes of the vehicles, the LiDAR, the radar, and cameras. And then in addition, as the autonomous technology develops, there's going to be more and more V2X, so V2 something, right? V2V, V2 vehicles, so vehicle to vehicle. So that could be a vehicle is up a couple miles up the road, warning another vehicle that there's a thunderstorm approaching and be careful, right? You can have vehicle to infrastructure where your traffic light is telling the vehicle that the traffic light's about to turn red or turn yellow. Vehicle to P, V2P, to pedestrians and devices saying, hey, I'm crossing the street, watch out, right? All this will happen, and then with the help of 5G, there's also going to be a massive amount of data that's being transmitted back and forth between the vehicles, the infrastructure, the pedestrian, and devices. So these control units, they need to process this information and then provide those inputs to the driver modules for, say, steering, braking, and powertrain. And all these electronics, they'll be critical, and depending on the location, they'll need some sort of protection. So what are some of the challenges facing design engineers and OEMs today and in the future? Well, from a protection point of view, electronics and corrosion and hazardous environments, they don't mix very well. As I showed previously, vehicles are gaining more electronics every day, and they're also relying on electronics for basic and advanced functionality. They're not spared the harsh environments they've always been exposed to. Nothing's changed with the vehicle operating environment, right? It's still cold, it's still hot, it's still wet, it's still salty. Nothing's changed with the environment. The electronics have changed. Inside the vehicle, there's threats such as lotions, hand sanitizers, liquids, sugary drinks. They can all wreak havoc on unprotected components inside the vehicle. Exterior hazards such as oils, fuels, rain, salt, mud, humidity, all those combined with an unprotected PCBA can render a vehicle inoperable in seconds. So when more electronics and typical vehicle corrosive environments combine, it creates significant challenges for design engineers and OEMs. So additional challenges with keeping safety in mind, as this is the most important factor for consumers and also OEMs as they're looking to be a top safety pick and have 5-star rating. So as mentioned, today's vehicle PCBAs, they help drive nice to haves, such as power windows, heated seats, to more critical components, such as drivetrain and autonomous vehicles. As you can see in the chart, the market for electronics has grown significantly over the last 8 years, with an increase in safety and ADAS systems. This trend is expected to continue as we move closer and closer to level 4 and level 5 of autonomy. The reliability of these electronics becomes increasingly more important to last the life of the vehicle under harsh operating conditions. Failure from corrosion or short circuit, it's not an option. If a power mirror stops functioning due to moisture, it's a headache. But if a safety system fails due to corrosion, it could be a real tragedy. So where seals, glues, traditional conformal coatings were acceptable protection methods previously, alternatives like thin film coating should be included in the designer's toolbox. Imagine a seal being compromised on a LiDAR or blind spot radar module with an unprotected PCBA. This could allow ingress of salt spray. From there, it won't take long for the salt to cause corrosion and eventual failure. leaving the level 4 or level 5 autonomous vehicle essentially blind. So over the years, the automotive industry has developed solutions to protect today's vehicle electronics, but are they able to protect tomorrow's ADAS and critical components? So automotive electronics have never been more complex or critical. Here on the screen, I'm showing a telematics ECU, an automatic gearbox ECU, and a park assist ECU. These are complex PCBAs that didn't exist too long ago. They have protection, they're conformally coded, but is that enough for tomorrow's level 5 vehicle? The complexity of the modules are always increasing, the space is always decreasing as more and more devices are added to the vehicle. So it's a balance of putting more in a smaller space, and that's a real challenge. I remember some of the projects that I was involved in where you get the envelope for your device, where it's going. You go through your CAD, you're designing your mechanicals, you're designing your electricals. You go back again, now there's a duct or there's another device or there's a wiring harness in the way, and you have to go back in and redesign. There's devices that automotive is starting to use. These all have BGAs, and they help reduce the board size, but again, they add challenges in board layouts and manufacturing. And depending on your ECU location, sealing and or conformal coating may also be required. And all this needs to happen at best cost and lowest weight. As we all know, the automotive industry is extremely competitive. So in addition, traditional conformal coatings, they may also stress sensitive components like these BGAs. And traditional conformal coatings may not even be conformal enough for tomorrow's safety critical devices. Dominique will talk more about conformality in her presentation coming forward. So for these reasons, designers and OEMs, they're finding limitations in their ability to sufficiently protect these complex boards with traditional methods such as mechanical seals and conformal coating. I'm going to turn the time over to Dominique. Dominique, in your engineering career, what limitations have you seen with traditional protection methods?
Thanks, Calvin. As you previously mentioned, the hot and harsh environments that vehicles operate in are not conducive and sometimes catastrophic to the growing electronics found in the vehicle. I want to delve more into the technical aspects that engineers and designers face when designing for harsh environments. The average lifespan of a car is now around 12 years, which represents a slow and steady climb over the last several decades. That's because cars are smarter, better designed, and better built than they were 20 to 30 years ago. Automated factories have led to high precision manufacturing, parts are more reliable, electrical systems have replaced mechanical systems, which reduces breakdown and improves engine efficiency. Technology is the main reason for long-lasting vehicles. Most improvements in efficiency, emissions, safety, reliability, and longevity are from microprocessors, microcontrollers, and extensive unseen networks on board the cars themselves. Such improvements are increasing not only cars' lifespans, but manufacturing warranties. 3 years, 36,000 miles used to be standard, but now we're seeing more 10-year, 100,000-mile warranties becoming common. Standard and electric vehicles need to withstand a range of environments, including the salty air and heat at a beach in Florida, all the way up to frozen winters in Canada or Norway. Not only do they need to be able to handle temperature fluctuation in a lab setting, but also in a real-world environment. Inside the vehicle, you have components that could be exposed to coffee, sunscreen, bug spray, or especially right now, hand sanitizer. And I can tell you from experience, heat and foreign substances rarely mix well when it comes to the interior of a car. Under the hood is not any better since it gets much hotter and you end up with solvents such as washer fluid or oil that can cause a reaction when those components are exposed to heat. For years, OEMs have been using traditional mechanical seals and thick conformal coatings to address protection. But as automotive electronic assemblies continue to become more sophisticated in both functionality and reliability, the need for better, thinner, and lightweight protection is more critical than ever. Key requirements and challenges for automotive manufacturers include weight reduction, improved circuit performance, and enhanced device reliability, as well as resistance to a range of fluids, oils, and humidity. In many cases, seals need to be smaller and lighter now to account for the changing market requirements, and traditional seals are becoming cumbersome to use. Some traditional coatings like silicones are commonly used. Compared to parylene, silicones are an alternative that need to be carefully evaluated to ensure that they are properly cured to prevent outgassing. Mechanical stresses are also possible with silicones, especially when enduring those hot-cold cycles that you see from summer to winter. This means additional materials such as underfills or adhesive materials may need to hold the part in place. in case the silicone expands to the point of dislocating that component. And the other thing to keep in mind is outgassing from silicon manufacturing requires restricted areas of the plant specific to that process. So chemical vapor deposition, that process provides a biostable, biocompatible, and environmentally friendly process that requires no solvents or VOCs. There is no outgassing and only one ingredient is needed. There are no initiators or catalysts in the polymerization reaction, so the coating process is pure and free from trace ionic impurities. The raw dimer material starts in a powder form. It's then sublimated into a gas phase in our vaporizer, at which point it goes into the pyrolyzer, which breaks those larger molecules down into individual monomers. Then it moves over to our deposition chamber, which is under vacuum, where it will actually deposit that coating over the surface of everything inside the chamber, once again back into that solid form. This allows for multiple parts to be coated simultaneously and ensures uniform coverage. Instead of a powder, you now have a continuous film covering the entirety of that component. Areas that cannot be coated, we have to mask them off to protect them from coverage. We always need to double check our masking ahead of coating, since Parylene can completely penetrate spaces as narrow as 0.01 millimeters. Having a thin coating also means the risk of the coating stressing sensitive components is minimized. The exact parameters at each stage of the process are recorded and can be duplicated for each run, which cuts down on run-to-run variability. The deposition process itself is also done at room temperature to minimize stress on any of those sensitive components. All Parylene types are REACH, ROS, PFOA, PFOS-free, and Prop 65 compliant. There's also halogen-free and high-temp Parylenes that are available. All right, Parylene has many electrical, mechanical, and chemical benefits compared to your traditional conformal coatings. At HZO, we work with 3 types of Parylenes, C, N, and F. And overall, each of these Parylenes offer outstanding barrier protection against corrosive chemicals, high level of submersion protection, up to 90% lighter and thinner compared to maybe a spray or a dip coating, optically transparent, excellent conformality, and good dielectric strength. Parylene C is used commonly in many applications for its overall properties, but Parylene N provides that halogen-free alternative that seems to be becoming more and more common. This is just a quick comparison of Parylene compared to a handful of more traditional conformal coatings. This information will be available in the slide deck following the presentation for those of you who would like to take a closer look. So I just mentioned the dielectric properties of Parylene. As you may know, the dielectric strength refers to how well an electrically insulated material can perform. Dielectric strength is a number calculated based on the maximum electric field the material can withstand under ideal conditions before it breaks down and becomes conductive. As you may be aware, tests done under ideal conditions rarely reflect reality. That's where the longevity and chemically inert properties of Parylene come in handy. Even in a scenario that the product's been exposed to salt, humidity, gasoline, etc., we can still expect Parylene to perform under pressure. As more of our customers demand Parylene for their tough environments, we are expanding our testing program to include a comprehensive third-party test certification through UL. Under UL 746E, which includes severe dielectric breakdown and flammability testing, we will be acquiring independent test results. The cool thing about this test is there's 4 different types of environmental conditioning, which mimics those real-life scenarios to make sure that the data provides a real scenario for you. For automotive applications, an instance of dielectric breakdown could lead to a non-functioning component all the way up to a catastrophic failure. Having a material that is a strong dielectric is an important step in preventing these issues from ever taking place. Parylene can sustain an electric field without conducting electricity, allowing for the safe transmission of electrostatic lines of force through protected components. Parylene is able to withstand very large temperature changes, ranging from around 100 C to well below 0. You'll notice here that silicone also has a pretty decent temperature range, but requires a much thicker coating to meet IPC standards. Silicones encompass a large class of materials, so it's important to ensure that the one being used meets the desired requirements. While silicones can have decent chemical resistance, they're not able to keep up with Parylene, especially when considering the automotive grade. For example, we recently dunked coin cell batteries in salt water and artificial sweat solution, one coated with Parylene and one that was uncoated. Seeing how quickly the uncoated battery completely corroded looked like the beginning of a bad infomercial. In comparison, the Parylene was tested for days without issue, so it definitely has that chemical resistance for you. Regarding total cost of ownership, HZO can help, especially when it comes to recall issues. The numbers listed here show the percentages that the following situations can occur. Since Parylene coating is long-lasting, it is able to keep up with the life of the average car. The total conformality of Parylene can prevent corrosion due to salt, rain, snow, and all the other scenarios we've been talking about today. This keeps any and all high-risk modules functioning correctly during the car's lifetime. HZO has a yield greater than 99% when it comes to manufacturing. The repeatability of the HZO process ensures that the parts are done right every time. Designing a thin film coating into the drawing from the beginning rather than adding it later in the build can optimize protection. HZO has an automated masking and demasking, which significantly reduces the risk of human error. And on top of that, the incoming outgoing quality procedures in place ensure that reworking is successfully completed on any parts that do not meet HZO's quality expectations. All right, what are the manufacturing benefits of HZO? Because our coating chambers are a meter cubed, we believe that they can significantly fit more substrates in one run than any of our Parylene competitors. We've moved away from the smaller circular chambers to this large chamber size to maximize our efficiency. Having a longer chamber in turn reduces turnaround time from start to finish. This also means that much larger parts can be Parylene coated, which may not have been an option before. The quality assurance at HZO guarantees that parts produced will meet our quality standards to ensure functionality and protection. There are a couple of different options for using HZO. The most popular is our turnkey solution, in which we provide the people, equipment, material, and the expertise. It's also possible to have parts shipped to one of our centers of excellence to coat and return parts. And the third option would be to install HZO equipment at the tier 1, 2, 3, etc., and train their operators to use our equipment. That's about all I have for today. Calvin, you want to finish us off?
Sure. Thank you, Dominique. That was really informative. So to wrap up the presentation, the question is, why choose HZO for your protection needs? Well, we have a long, proven track record of on-time deliveries with some of the biggest names in the electronics industry. We have various business models that Dominique just mentioned. So we have coating only, coating as a service, and factory. We design and build our own equipment in our facility in Hungary. Our equipment can handle large automotive volumes, and we also have a global footprint. So with that, we'll go into the Q&A session, and if you'd like any more information, please don't hesitate to reach out to us.
All right, thank you, Dominique and Calvin. With that, we'll move to the Q&A portion of the presentation. As I mentioned earlier, please feel free to submit them through the Q&A box or the chat. We're monitoring both. But we'll start off with the first question. Could you go into more detail about the cube chambers?
Sure. So it is a meter cube all the way around, and within that cube we have racks, and we have different ways we can set it up. So depending if you're trying to go to a very large part or a very small part, we can configure that meter cube to make sure that we can successfully coat whatever's in there.
All right. The next question is, how is Parylene sustainable?
So Parylene is, like we've talked about a little bit today, very chemically inert and can handle a lot of different scenarios. So we've done testing, and Parylene can last up to 10 years, if not more, in an elevated environment of around 80 C.
Our next question is if you can repair Parylene.
Repairing Parylene is a little bit more difficult because it is very conformal. So if there was an issue with a section, we would probably take that off via ablation or something else that's a mechanical removal method. And then depending how big of the area needed to be coated, we could recoat, or we could just do a touch up with a traditional conformal.
Great, thank you. Our next question is, what is the cost of applying Parylene?
I'll take this one. So there's a lot that goes into the development of the cost. It's not really a simple cost X. There's this, Dominique mentioned, there's the different types of parylene. There's also the thicknesses ranged anywhere from 12 microns to 50. So that plays a part of it. The application, whether it's on engine or where you have much more severe conditions, or if it's inside the vehicle. So there's a lot of different options that come into creating the end price on this. So best is to get with us and we can discuss, understand your application more, and then we can develop a custom quote for you.
Thanks, Calvin. Our next question is, it looks like you serve other industries like consumer electronics. How do we know we can trust you for mission critical coatings?
All right, I'll take this one as well. So yeah, we do mission critical coatings for a few industries. We have applications that we serve. We're also within automotive, medical, even military. So none of those were, the failure is not an option in any of those. So at HCO, we quickly configure our equipment and processes to try to meet all the requirements. So we're not really limited by industry when it comes to solutions. And we tailor the solutions around the business and their needs, regardless of the industry.
Great, thank you, Calvin. That is all the questions that I have in the chat box. If there are any others, please submit them now. Okay, can you speak more about temperature?
Yeah, sure. So the temperature does affect parylene to an extent. If we're at room temperature, say, I mean, parylene can go for years and years and years. If you're getting up to a certain, I don't know, over 100, 150 C, you need to be careful with what parylene you're selecting and what environment it's going to be in, if that's like a consistent temperature or if it's going to be more of a cycled temperature.
Okay. Our next question is, how to adhere parylene to low surface energy surfaces?
So actually we do like a plasma cleaning treatment to increase the surface energy of a part prior to coating it. The other option we have is we'll add an adhesion promoter into the chamber. So, you know, you have your plasma, your adhesion promoter, and then the parylene on top of that, which helps it stick to something that might not necessarily want to get stuck to.
Okay, our next question is, does parylene help with lightweighting?
Absolutely. It is very thin. I mean, we're talking no more than 50 microns usually, and it's very lightweight. So instead of having something a little bit clunkier like a steel or silicone, it absolutely will help you get a lighter coating and a lighter part overall.
Okay. With that, are HCO coatings better in cabin or outside?
They need to be encased, right? So, I mean, it can be in a component that's in the cabin. It can be a component that's in the engine. We just don't want parylene to be on the outside of thing because abrasion would be a concern in that case. As long as it is fully encased, it can go pretty much anywhere.
The next question, can coatings be used on sensors?
That is a great question. I guess it depends if the sensor is going to be interfered with. So it kind of depends what sensor we're talking about, right? If it's something that needs to be optically able to see, yes, parylene is optically clear, but I mean, it could mess with that sort of thing. So that would be more of a case-by-case basis to see what we need to do with that.
Okay, and we'll do, the next question is this a quick process or does it take a long time?
So that depends on kind of how thick we're going and what we're doing, right? So if you're doing a very thick coating, yes, it will take a long time, but a long time could be 16 hours. But you could also fit, you know, thousands of parts in one run. So you kind of have to think of it more as a batch process. But so you'll have the assembly line up to it, get them all coated, and then they'll continue on, and then we can kind of stage it so that you don't have a lag time. But I mean, we can have a shorter coating run or longer, but I mean, you're not going to see anything over, I'd say 20 hours. Alvin, do you want to add to that?
No, I think that's it. Really does depend on the thickness, and I think and that's really how we try to work it backwards from the line takt time, and then you can balance the line through, as Dominique said, by adding number of chambers and trying to do it as a batch size to continue with the line as you're going forward. So after you're done with PCBA, before you go into final assembly, we can try to match the takt time based on all the parameters involved.
All right, with that, we're going to close out. After later today and tomorrow, you'll be receiving the recording of the presentation as well as the slide deck, so be on the lookout for that. If you have any additional questions, please feel free to reply to that email or reach out to us on our website, and our team would be happy to meet with you to discuss your specific applications and how we can help you. Thank you for joining, everybody.